Assalamualaikum warahmatullahi wabarakatuh. Good day everyone. Okay, I would like to actually explain on the stiffness method, stiffness matrix method analysis of trust. So we are referring to example 14.1 okay, Hibbeler textbook. Okay. Okay, let's see the question. So this is actually the question given in the textbook. So as I explained previously in my previous lecture, so in order to analyze trust using stiffness method, so what we need to do is we have to make sure that the trust must consist of node number. Okay, must have node number. So this is the node number. There are three nodes in the trust. Okay, this is trust with three nodes. Okay, so node number, and then uh, we have to have element label. So element number 2, this is element number 2, this is element number 1. So there are two elements where element 1 consists of element 1 joining node number 2 and node number 3. Node number 2 and node number 3. That is node number 1, element number 1, and element number 2 joining node number 2 and node number 3. Okay, so that's the second thing that we need to make sure. Okay, number 3 is we have to put the arrow. We have to have the arrow. Okay, if don't have, we have to put the arrow in in any direction that we like, but it must be parallel with the member. Parallel with the member. Okay, why we need to do that? Because we will identify near and far end condition based on the arrow, because the arrow is always going to the far end, so this will become near for element number 2. So same goes to element number 1. The arrow is going towards the far end, so node number 3 will become far, node number 2 will become near. Okay, so after that we have to put the coordinate. We have to put the coordinate. This is the coordinate. This is the coordinate. Okay, so to identify or to put coordinate, we have to choose one as origin. Okay, we have to choose one as origin, and by choosing node number 2 as origin, so we will have node number 1 and node number 3, which has positive coordinate. So we get 3 0 based on origin node number 2, and we have 3 4. We have 3 4 for node number 1. Node number 1. Okay. So these are the 4 things that we need to make sure. Okay. Okay. Listed or highlight in the diagram. Okay, number 1 is node number, number 2 is element number, number 3 we have to make sure that the elements have the elements has arrow which is parallel to the member. The arrow is important because from the arrow we can identify which node become near end, which node become far end, and then the coordinate, okay, we have to choose one node as origin, and we label the other coordinate based on the origin that we have chosen. Okay, number 5, the most important part is degree of freedom. Degree of freedom. So degree of freedom, we have to label according to unconstrained and constrained system. We have to label according to unconstrained and constrained system. Okay, unconstrained and constrained system. So we can look at the label shown here. This is for the degree of freedom. So remember the sign convention for trust uh, is x and y direction. X and y direction means that there are 2 degree of freedom per node. There are 2 degree of freedom per node, but we have to put and to label start from unconstrained. We have to label start from unconstrained. And when we have one, two, and three nodes, when we have three nodes, we have in total six DOF. And these six DOF we have to divide into okay Q, U, and DU. So what is QU? QU is unknown reaction. So based on this diagram, there are four unknown reaction because of two pin support. So this is four. Okay, so when unknown reaction equal to four, okay, the remaining is two. Okay, to get total six because total the must be six. And DU or unknown displacement is actually located at DU located at unconstrained and QU located in constrained system. So when we label, we should label 1 and 2 and followed by 3, 4, 5, 6. Okay, located at unconstrained at constrained system. Okay. So, okay, now we have checked the diagram is now complete with five important criteria: node number, element number, the arrow, the coordinate, as well as the degree of freedom. Okay, let's look at the question. Okay, so for the question based on example given in the textbook, it is example 14.1. 14.1. So the first question, establish element stiffness matrices. Establish element stiffness matrices K1 and K2. K1 and K2. Okay, we use small letter because it is four element. We use small letter because it is four element. K1 and K2 representing element stiffness matrix for element number 1 and for element number 2. Okay, and we use global coordinate system. And after that, we have to combine K1 and K2 to get the structure stiffness matrix, and this is capital K. Capital K. Okay, how to do this? What we need to do is we have to analyze separate elements separately. We have to analyze element 1, K1, and we have to analyze element 2, K2. Okay, so actually we are given the formula. It is actually a simple formula where we have to identify lambda x and lambda y for both elements, element 1 and element 2. Okay, let's say when we want to analyze element number 1. Okay, element number 1 is this. Element number 1. Okay, node number 2 and node number 3. So this is the arrow. Okay, this is the arrow. This is 0, 0. This is 3, 0. Okay, so the length is 3 meter. So in order to establish in order to calculate lambda x is actually for lambda x, we just need to focus on the x value for lambda x. So for x value, we refer to 3 far. This is far, this is near. Okay, it must be far minus near. So it is far minus near, 3 minus 0. 3 minus 0, we divide by L. So what we get is 1. 1. So 1 is the value for lambda x. And for lambda y, we focus on coordinate y. Lambda y, we focus on coordinate y, so it is 0 and 0. It is far minus near, so it is 0 minus 0 divided by 3. So the answer is 0. The answer is 0. So we use 1 and 0, lambda x and lambda y value, and we substitute into the formula. It is AE over L. So this is L. L for element number 1. So based on the formula, this is what we get. And what we need to do after this is we have to remain AE as constant outside the matrix. So we get the stiffness matrix for element number 1 as this. Okay, this is the matrix. The matrix. What most important is the degree of freedom label. This is the label. Degree of freedom label. What does it mean? This is the position. Okay, means that this is the position. So inside the diagram just now we have 6, 1 until 6. Okay, so we need to label the degree of freedom for element number 1. We need to label, we need to label degree of freedom for element number 1. Looking at the arrow, looking at the arrow. Okay, and we need to label start from near. This is near, this is far. It is, okay, by looking at this, it is 1, 2, 3, 4. That's how we spell the degree of freedom for element number 1. Again, so we label, looking at the arrow, we label start from near to far. So we label as 1, 2, 3, 4. Okay, this 1, 2, 3, 4, we have to write like this. 1, 1, 2, 3, 4. Okay, and this is 1, 2, 3, 4. So this is actually the answer, the element stiffness matrix for element number 1. Okay, now we settle element number 1. We move to element number 2. We move to element number 2. For element number 2, so from the diagram, okay, from the diagram, okay, from the diagram, okay, this is element number 2. Okay, element number 2, joining node number 2 and node number 1. The arrow is like this. Okay, so from this we know that from the arrow, this is near end, this is far end, near and far. And from the coordinate, this is 0, 0, this is 3, 4. Okay, from the coordinate, we can, okay, determine length. So the length is 5 meter, 5 meter. Okay, and we continue with uh, calculate the lambda x and lambda y. So always remember, when we want to calculate lambda x, we focus on the x coordinate. X coordinate is 3 and 0. It is far minus near, that is why we get 3 minus 0 divided by 5, we get 0.6. And to calculate the value, for y value, okay, for y value, so it is 4 minus 0 divided by 5, so we get 0.8. So this 0.6 and 0.6 and 0.8, we have to substitute into the formula given. Okay, so the formula is AE over L. This is L. This is L for element number 2, 5 meter. So the value inside this, okay, we get from formula. And finally, okay, we should write like this, because we want constant AE, because we will sum K1 and K2. So we have to have this in terms of AE, and this one also in terms of AE. So this is K2, but what most important is degree of freedom label. Label what? Label of degree of freedom. Label what? Label of degree of freedom. So how to read this label? Okay, how to read this label? Refer back to the diagram here. Okay, number 2. Okay, the label. Okay, to spell out the label. So this is near end, this is far end, So we should spell out like this. It is near to far. Near we have 1, 2. Far we have 5, 6. Near we have 1, 2. Far we have 5, 6. Okay, near we have 1, 2, far we have 5, 6. So it is 1, 2, 5, 6. It is 1, 2, 5, 6. So it is 1, 2, 5, 6. 1, 2, 5, 6. 1, 2, 5, 6. Okay, now we have K1 and K2. We have K1 and K2. Okay, now to establish the structure stiffness matrix, this is the structure stiffness matrix. We label by using capital letter. Okay, we need to combine K1 plus K2, but always remember that K, the capital K, represents structure stiffness matrix must 6 by 6 because of 6 degree of freedom in the truss. So what we need to do is, okay, for the structure stiffness matrix, we must remember that we must write the value in order. In order means it must be started at 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So to have this, what we need to do is at position 1, 1, position 1, 1, we get 0.405 from this. We get K1 from 0.012 plus with 0.333, so we get 0.405. Okay, for position 1, 2, for position 1, 2, okay, we get from 1 to 0.096 only. Okay, so it is 0.096. And then the next value is at position 1, 3, it is negative 0.322 because 1, 3 we get from K1. This is position 1, 3. So that's why we get 0.333. Okay, 1, 4 is equal to 0, 1, 5. 1, 5, okay, 1, 5, 1, 5. This is 1, 5. Okay, negative 0.072 and 1, 6 is negative 0.096. Okay, so and because this is metric and metric is always symmetry. So what we get is actually okay. This value is actually equal to this value because it is matrix and matrix characteristic, okay, is symmetry. Okay, matrix characteristic is symmetry. Okay, so we continue to calculate the value for position 2, 2. This is position 2, 2. So we get from 2, 2 is 0.128 plus 0, 2, 2 is 0. So that is why we get this as 0.128. So we do the same thing to find the value at each position from K1 and K2. Okay, for example, if you want the value for position 4, 5, so 4, 5, this is 4, 5, this is 4, 5, so find 4, 5 in K1, there is no 4, 5. Find 4, 5 in K1 and K2, there is no 4, 5. So when there is no 4, 5, so the value is 0. For example, if you want to calculate the value for 6, 6, 6, 6, if you want the value for position 6, 6, so find 6, 6 in K1 and K2. So in K1 and K2, 6, 6 position equal to 0.128 and there's no 6, 6 in K1. So it is equal to 0.126. So so this is the final answer. The final answer, it is the structure stiffness matrix. Okay, this is for the truss. For the truss, okay, for this truss where this truss has two pin support. Okay, two pin support. Okay. Okay, before we end this session, I want to highlight certain important things. Okay, number one, number of degree of freedom equivalent to 6 because of 3 nodes. 3 nodes two representative degree of freedom per node. Okay, QU or unknown reaction. Okay, there are four because we get from pin support. There are two pin equal to four. So it is equal to four, and unknown reaction occur in constraint system. Okay, so in opposite condition, if QU is 4, the remaining will be put under DU representing unknown displacement, and unknown displacement is located in unconstrained system. Unconstrained system. Okay, so label degree of freedom for unconstrained. Okay, what we need to do is we have to label unconstrained first. Label unconstrained first because displacement will be determined first. Okay, determine displacement will be determined first. Then only we can calculate QU from force displacement equation. So that is why from this, after we identify that 2 is unconstrained, we label 1 and 2 at node number 2, then only we label 3, 4, 5, 6 at pin support. Okay. So this is actually the formula we use to calculate K1 and K2. Okay, and this is actually uh, the important things that we need to make sure exist in the free body diagram. Okay, as I explained, node number, element number, the arrow, because we identify near and far end from the arrow. Okay, we have to put the coordinate, okay, based on the global system, and finally we have to label the degree of freedom. Okay, from unconstrained first and then followed by constraint. Okay, so that is actually the answer for example 14.1 Hibbeler textbook. Okay, so before I end my session, I want to ask you one question. Okay, if the pin at node number 3 is changed to roller support, can you spot any changes in degree of freedom numbering and the structure stiffness matrix? Okay, so please try to answer this question, and thank you. We will meet again in the next session. Assalamualaikum warahmatullahi wabarakatuh.